Okay, for this video we're going to do linear curve fitting. So, and you've sort of all done the experiment where you've taken data in Excel and plotted it, and then you right-click the graph and said add trend line. But maybe you didn't really know what it was for or where it came from, and that's what we're going to do in this video. And at least for instrumentation, the reason why it's used primarily is for calibration. So this is calibrating sensors. And so this is really important because the idea is that you have some measurand, right? And then you have some sensor, and then you're going to get some signal, and you're probably going to put that through some filter to filter out noise, and then you're going to get an analog voltage, right, or a resistance or a current or so whatever you're measuring some sort of circuitry, right? I mean, you remember in all the other chapters, every sensor that works operates on some sort of voltage thing. So if you're measuring wind speed, you're measuring pressure, or you're measuring angular velocity with a photocell, with a rotary encoder, or light with a photocell, like everything is current or voltage. And that's going to go through some analog to digital converter, and that's going to go to your computer, okay? So then you're going to end up with data. So the example in the book is that your measurand is displacement, and this is in meters, and it goes through all of this, and at the end of the day, you get this analog to digital converter is going to give you DO, and then you multiply this through a gain block where you do your voltage range over, sorry, it's not your voltage range, it's your voltage range over your bits, right? However many bits you have on your A to D, and that's going to give you a voltage signal. Okay? So what you're going to do when you do your experiment is you're going to move the, what is this, an LVDT? Yeah, an LVDT. This is a linear voltage displacement sensor, linear variable differential transformer. So it just means that there's a slider hooked up to a potentiometer, and as it moves, it changes the resistance, and you run a current through it, and you can measure the voltage drop. So what you do is you make a table like this, and you're going to measure something with a ruler, and in this case they get 0, 0.5, 1.0, 1.50, 2.0, and 2.5. Okay, and that's in centimeters. And I guess in this case, whoever designed the LVDT designed it well, and the voltage that you get at 0 was 0.05, and you might be wondering, well, if the sensor is at 0, right, like if it's all the way in, why did you get a voltage reading? Well, I mean, you got sensor noise, sensor bias, all of these different things. It's why you take multiple trials and multiple data runs so that you can average everything out. In this case, I'm assuming that this person has taken this data point like 10 or 20 times, and this is the average of those 20 trials, and then he moved the sensor half a centimeter and then measured the voltage again and averaged them all together. But anyway, so you're going to get this table of data, 0.52, 1.03, 1.5, 2.0, and then 2.56, okay? So then the question is what I want is, what if I don't want to use the ruler? Like if I have the ruler, great, but it would be nice if I had a way to take my voltage reading and then multiply it by some slope and some intercept and get L, right? This is what I want. I want to fit it to a line where I don't use the ruler, I put the sensor on there, I measure the voltage, and I plug it into this equation and I convert to length. Okay, that's sort of my goal here, right? If you have 2 data points, you really only need 2 data points to make a line, okay? So if you were doing this the easy way, you would take this point here and this point here, right? And you would create 2 equations, okay? So you would say L1 equals 0, L2 is 2.5, you would say V1 was 0.05, V2 was 2.56, and then you would create 2 equations, so you would get L1 equals M, V1 plus B. My unknowns are M and B, right? Slope and intercept. And L2 was M V2 plus B. And then you could just solve this for one or the other, right? So you say L1 minus MV1 is B, and then you could say L2 MV2 plus plugging B into the second equation, L1 minus MV1, and then you get L1, L2 minus L1 over V2 minus V1 equals M, and that should be no shock to you, it's just the slope formula. So if we draw a line here, we've got voltage on the x-axis, we've got length on the y-axis. So at a voltage of 0.05, I'm at 0, and then at a voltage of 2.56, I'm at 2, and I basically fit a line like that. This is my slope n, it's the rise over run, right? That gives me my slope. And then if I have m, I could just plug this in and plug it into here, and this would give me my intercept b, okay? So you could just take two data points. You could just say, bring it all the way in and measure it, and then you could just bring it all the way out and measure it again, and then just use those two data points. But what about all these points here? Or what if you did multiple trials? You only need two equations to get two unknowns, but what if you have 10, what if you have, in this case, 1, 2, 3, 4, 5, 6. You have six data points, which means you have 6 equations. So you have the number of unknowns is 2 and the number of equations is 6. So it means that you have what's called an overconditioned problem. And you have more equations than you have unknowns. Okay, so what do? Your book has a fancy formula for a regression equation. I don't really like that equation because A, I don't know where it comes from, and B, you can't use it for nonlinear equations. And so I'm going to show you what's called Gauss's optimization routine, and hopefully that will make more sense. So I'm going to take a picture of the board here and come back. Where's my phone? Here we go. Okay, so I'm going to keep the data, but I'm going to erase everything else. And what I'm going to do is I'm going to look at my equations. What I really have is I have L1 is mv1 plus b, and then I've got L2 is mv2 plus b. I've got L3 is mv3 plus b, so on and so forth, all the way down to L6 is mv6 plus b. And this is L1, 2, 3, 4. This is all of the L's, and these are all of the B's. Or sorry, V's in Victor, okay? If you look at this, what I can actually do is I can put this into a matrix, and I can say, give me all of the L's into one big matrix and call this L. And then what I'm going to do is I'm going to put this in matrix form such that I've got M and B here. So this here is my vector of unknowns, M and B, and then what goes in here? Well, L1 is equal to, first of all, how big is this? This is a 6 by 1, right? This is a 2 by 1. So in order to get my inner product to match, this needs to be a 6 by 2. So it's 6 rows, 2 columns, okay? So if you look at this equation, M times V1. So M times V1, that means V1 goes here. So it's 2 columns, right? So what gets multiplied by B? Well, 1. What about L2? Well, that's just going to be V2 and 1. And then you keep going down, you're going to get V6 and 1. And what I do is I call this matrix H. This is a vector, it's a 6 by 1. This is a 2 by 1. This is a matrix, so this is a 6 by 2, like that, okay? And so now you have a vector equation where L is H theta, okay? And so the question is you know L and you know H. Those are your knowns, right? You know all the V's, 1 is just a constant, and you know all your L's, you don't know M and B, so you need to solve for theta. Now you might say, okay, we'll just divide by H. Well, the problem is you can't because H is a 6 by 2. You can only divide by square matrices. So what you need to do is you actually need to multiply the left-hand side by H transpose. So H transpose is a 2 by 6, and you multiply that by L like this, and you get H transpose H times theta. And so what did that do? Well, this is a 2 by 6, and this is a 6 by 1. So if you multiply these together, you actually just get a 2 by 1. This is a 2 by 6 times a 6 by 2. And so if you multiply those together, you actually just get a 2 by 2 matrix. And that's good because it's all, not only is it small, but it's also, you can divide by it, you can invert it. And this again is still a 2 by 1. So now I can just divide by this HH transpose, and what I get is I get that H transpose H inverse H transpose L is equal to theta. And that, and technically it's a star, when you multiply H transpose by H, you're taking a 6-dimensional matrix and shrinking it down to a 2-dimensional matrix, and you lose a little bit of information when you do that. And so this might be cumbersome to do by hand, but if you actually look at it, like what is, let's write out what H is, what this is, right? H transpose is just all of my V's in 1, right? So it's going to be 0.05, 0.52, 1.03, 1.5, 2.0, and 2.56. And then 1 is just going to be 1, 1, 1, 1, 1, 1, right? And then you multiply that by H, which is 0.05, 0.52, 1.03, 1.5, 2.0, 2.56, and then 1, 1, 1, 1, 1, 1. And if you multiply this together, you get a 2 by 2, right? So you're going to get this row times this column, which is really just the sum of all of your V's squared. So I'm just going to call it sum VI squared, right? So it's the sum of all your VI squares. Then over here, it's going to be all of your VI's added together, so that's the sum VI. Over here, same thing, sum VI. And then over here, it's just going to be the sum of, or really it's going to be what? 1 plus 6. So it's just the number of data points you have, so n. Okay? And then that's a 2 by 2 matrix, and you just invert that. I'm not going to show you how to invert a 2 by 2 matrix. You can go watch another YouTube video to do that. But you invert this 2 by 2 matrix, and then multiply H transpose L, and you get theta. You're going to get two numbers, and that is M and B. And you're done. And so doing this by hand is actually not as hard as you think. If you look at the formula in your book for instrumentation, the formula is just as nasty as this. And the problem is you don't know where it comes from. Okay? And I guess after this, I'll probably not today, but eventually I'll probably post a YouTube video on how to do this in Python. And so if you get any data set, doesn't matter if you have 15,000 data points, you can easily do this formula and get a trend line. And that's why matrix multiplication is so nice. Doing this by hand, I would say only like 10 or 15 data points before it starts to get a little bit cumbersome. Cool. That's linear trend line fitting. I guess the only other thing would be the correlation coefficient. So let me take a picture of this real quick. Okay, so the correlation coefficient is used to tell you how linear your data set is, okay? So imagine you're given a data set, you're given a bunch of L's, and you're given a bunch of V's, and you have n data points, okay? And you run it through your optimization routine, you get theta star, and that gives you an m star. I think your book uses tilde. Yeah, sorry. Let's use tilde. So this is your estimate for m and b. And so this gives you an M and a B. And so what happens is that if you take your known data sets, if you do L tilde, L1 tilde, that's going to be M tilde V1 plus B tilde, right? You didn't, because you had more data points than unknowns, you didn't exactly solve for M and B, you got the best fit. You got the closest to your actual solution set. And so what they do is they call that L tilde, okay? So what you can do is you can say, well, all right, what I really want to do is I know this is what I wanted. I wanted L equals H theta. And unfortunately, I didn't get it. I got L tilde is equal to H theta tilde. This is what I got. And so the question then is, what is my, how linear is it? Like if I get a bunch of data points and I get something that looks like this, right? And I fit a trend line through it, that's pretty linear. But imagine if I got a data set that looked like, you know, like that, and you fit a trend line through it, like is it really linear, okay? And so the way you do that, you compute your R squared value, and it's equal to 1 minus, and it's, I like matrix multiplication, so it's basically L minus L tilde transpose, L minus L tilde. So you think about how big these are, right? This is a 6 by 1 minus a 6 by 1, sorry, L is a 6 by 1. So that means L transpose is a 1 by 6. And so if you do L minus L tilde transpose times L minus L tilde, that's going to give you a 1 by 6 times a 6 by 1, which is a 1 by 1, right? That's going to give you a 1 by 1. And so this is really just one number. And basically this is the difference. This here is called your residuals. Residuals. It is the difference between your fitted line and your data points. And what you do is you divide this by L minus L bar transpose L, sorry, yeah, I'm gonna do L bar. L minus L bar, where L bar is the mean of L, okay? And that gives you your correlation coefficient. They say, and I say they, I mean the people who are in charge of statistics, will say that you have a line if R squared is greater than about 0.8. Sometimes they give a range. If you have over 0.8 to 0.9, if you have something greater than that, you can say it's a line. If you compute your R squared value and you get 0.4, it's not really a line. You could fit a trend line to it if you wanted to, but if you're doing that, if you publish data that has like a 40% correlation coefficient and you say it's a line and the trend is up, like you're technically like, that's like unethical, I guess you could say. Okay, I think that's it. You can do some nonlinear curve fitting and things like that, but I think I'm just gonna leave it at that. That's linear curve regression, linear curve trend line fitting. I'm just using a bunch of buzzwords here. And like I said, I'll post an example in Python probably later this week. And then I assign some homework, so if you have any questions, post in the comments, and we'll go from there. Hope you have a good night.